Howdy, howdy, this is Mr. Potter. In today's lesson, we're going to be talking about translating and encoding our alphabet to different alphabet systems and vice versa. So, the idea of encoding is where we're going to be taking our alphabet and putting it into some coded system. We're going to talk about three such coding systems today. And then the idea of translating is that we're going to have a response or some type of output in that encoded system and have to translate it back to our alphabet. There's going to be two historical examples that we're going to be using, examples that were created in the 1800s that are still in use today, and then we're going to be talking about how computers do it nowadays. So I actually want to start with a brief discussion of Louis Braille. Now, Braille was a Frenchman, lived in the 1800s, was blinded before the age of 10 in both eyes. And when he went to school, he had the situation where the books were being read to him. He didn't have the opportunity to read them himself. And the reason he didn't have an opportunity to read to him is that the only way to read a book was to be able to feel a large letter C or see a large letter H. And they would have to feel these physical manifestations of the letters, and it was difficult. It depends on the font, it depends on the size, it depends on the sensitivity of the fingers. It's difficult, and so it was hardly used. What Braille did is he took a system from the Army, which used a system of 12 dots that the Army would use to read at night, and he modified it to a system of 6 dots, where these first 4 dots were used on a fairly regular basis, and these last 2 dots here were kind of modifiers. They would modify those letters. And so he took the French alphabet and translated each letter into this system of dots. So you'll notice here's A with a single dot, B with 2 dots in a vertical pattern, C with 2 dots in a horizontal pattern, D with 3 dots in this L-shaped pattern, E with these 2 dots diagonally, F with these 3 dots in a reverse L pattern, G using all 4 dots, H using the lower triangular 3 dots, I using a major diagonal I, 2 dots, and J using another set. He set these up so that they were distinguishable. I mean, if you're talking about a series of 4 dots, it's going to be hard to say that, okay, we're using these 2 dots in comparison to, say, using just these 2 dots. So what he did is he used a set of discernible sets of dots. So A through J used only the top 4 dots. K through T end up taking this exact same pattern of 4 dots. They're exactly the same except for this 5th dot down here. All the letters K through T have that 5th dot emphasized. And the letters U through Z, with the exception of W, do the exact same thing but with the bottom 2 dots. And the reason W is not here is because W is a letter that's hardly used in French. What they actually did with W is they made W the reverse of the letter R. And so what that means is that we have an alphabet in the Braille system, but we also have an alphabet in our standard English system. And so I can go letter by letter and compare them. I can look over here and say, okay, this one uses vertical dots. There's no bottom dots, so it's got to be one of these top 10 letters. And the only one that uses 2 vertical dots is B, so this first letter is B. This second one uses a dot in the lower left-hand corner, so it's got to be something on this 3rd row. And I notice that it's this L shaped with the dot down here, and so that matches with R. The 3rd letter here, I notice no dots on the bottom row, so it's got to be something on the top, and I just see a single dot, so that's going to be the letter A. I see same thing here, no dots on this bottom row, but I see these 2 diagonal dots, so that's going to be I. And then I see these letters here are all the same. They have the dot on the 3rd row, so it's got to be something on this K through T, and L seems to fit. And then I have these diagonals, but again, no dot here down on this bottom row, so I've got E. And so what happens is that what we've got here is the word Braille in Braille. So we have this ability to translate from one alphabet to the other based on the patterns that we recognize. And I can do the exact same thing by having a word like translate and have to translate it into Braille. So I notice the letter T is on the second row, so I'm going to have one dot here. And I notice that T has this other pattern, so I'm going to have a dot here, a dot here, and a dot here. So that would be the letter T. Now I need to do the letter R, which is also on this second row, so it has a dot, that only one dot on the bottom row, and it uses this set for the R. A is on the first row, so it's only going to be a single dot. N is on the second row, so it's going to have that bottom dot as well as these three dots here. So top row, top right, and center right. Got the letter S, which is on this second row, so that's going to be an S here, and that uses these position 2 and 3 dots. I've got the L, and the nice thing about L is that L actually looks like an L, a straight line up and down. A has a dot in this position. T we've already done up here at the beginning, so I can take what I remember. And E, which uses these two dots. Again, no dot on the bottom row because it's one of these first 10. So we have this ability to translate from our English alphabet to our Braille alphabet, this encoding. Getting to this special alphabet here, this is my process of encoding. But then if I want to get back, this process of getting back is actually translating. So I'm doing encoding and translating. And I can do this with the Braille alphabet because each letter in the English alphabet has a corresponding symbol in the Braille alphabet. And that idea of translating between the two is also going to work for our second example, which is the example of Morse code. Now, Morse code was invented by Samuel Morse. It was invented during his time when he was working with the telegraph system. And the telegraph is this electronic system that sent on and off signals. And he needed a way to transfer the alphabet. And he needed to do so in a way that the letters were unambiguous. They didn't interfere with each other. And so he used a series of two different types of signals. He would have a short signal, and he would have a long signal, something that we call a dit or a d and a da. So we would have these two different types of signals, dits and das. And by using various combinations of these, he could translate letters from our English alphabet into this electronic alphabet. He could encode them and then translate them back from the encoded version. So, for example, here is Morse code, and you can see the dots represent the d sound, and the long bars represent the das. And so what I can do is look at this, and the first letter I see over here has 3 dots and a bar. So if I look for 3 dots and a bar over here, I'm going to see that's the letter V. So if I put the letter V here, now I've got 2 dots here. 2 dots here is going to be I. I see a dash dot, dash dot. So if I look for dash dot, that's C. Then I've got a single dash. That's going to be the letter T. Then I've got the dash, dash, dash. That's going to be the letter O. Then I've got dot, dash, dot. That's going to be the letter R. Then I have dot, dot, and that's going to be the letter I. Then I have dot, dash, which is A. And then I have dash, dot, which is N. And so this actually spells out the word Victorian. And for the longest time, and even nowadays, we consider the telegraph to be an example of the Victorian internet. So during the Victorian age, during the 1800s and the early part of the 1900s, the telegraph allowed us to transmit information, messages, at the speed of light in a time when most letters had to be carried on horseback to the nearest town or through some type of wagon. And getting stuff across the ocean instead of a telegraph taking several minutes to go across the ocean, you would have to send it by a steamship, and it would take several weeks to get across an ocean. So the idea of the Morse code and the telegraph in general just completely reinvented the way that we talk about communication. And it's the ideas that came from this time that allowed us to even have the expectations that we do today with our instantaneous messaging that we have. Now, what I've done here is I've translated from the encoded version. I've got this encoded version up here to our standard alphabet, but of course, we can go backwards. So I can take the word telegraph. I look for the letter T, and the letter T is a dash here. I see the letter E, which is a single dot. I see an L, which is dot, dash, dot, dot. So I do dot, dash, dot, dot. I've got the letter E, which is another single dot. I've got a G, which is dash, dash, dot. I've got an R, which is dot, dash, dot. I've got an A, which is dot, dash. I've got a P, which is dot, dash, dash, dot. That should be a dash here. Dash, please. Dash, thank you, and a dot. Let's erase that so I can get that to look a little bit better. So that's supposed to be a dot, dash, dash, dot. And then I have the letter H, which is 4 dots in a row. So that would be dot, 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 dot. Let's fix that. Dot, 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 dot. So we have this ability to translate back and forth between Morse code, where we can encode our alphabet into these electronic signals, and we can translate back from the Morse code into our regular alphabetic symbols. And both of these were used during the 1800s. Both of these were used for different clientele. One for people who couldn't read the printed text and therefore needed a more tactile version, and those who needed to transmit messages over great distances. So this brings us to our third system, which is ASCII and Unicode. Now, ASCII was originally invented in the 1960s as a way for teletype machines. If you've ever seen the footage of old newsrooms and you've seen those machines that are printing messages and they're making that sound in the background. The ASCII was the way to transmit messages electronically. It really was the successor to the telegraph in that it allowed machines to completely do the translating rather than humans to do the translating. And in the 1990s, we came up with a more advanced version of this. In the 1990s, we came up with a more advanced version of this called Unicode. And the reason we have this Unicode is because not everyone uses a Latin alphabet. Not everyone uses the A through Z that we're familiar with. If you look at the Chinese or the Japanese or the Korean or Arabic or a lot of the languages that are used in India, or if you look at Hebrew or if you look at Arabic, there are a lot of different alphabets out there other than just our standard A to Z. But both of these codes, the ASCII code and the Unicode versions, work very well, and they are exactly the same for the version of the alphabet that we're going to be using. So I've got this table over here, and you notice that this table goes from 0 to 7 because it's dealing with this binary. There's 0, 0, 0, there's 0, 0, 1, 0, 1, 0 is how we'd write 2, 0, 1, 1 is 3, 1, 0, 0 is 4. So I see these values, and then I see these rows down here, and these go 10, 11, 12, 13, 14, 15. So that looks a lot like our hexadecimal that we were talking about. So this would really be A, and 11 would be B, and 12 would be C, 13 would be D, 14 would be E, and 15 would be F. And what that means is that I could look over here and I can say, oh, here's letter A. It's in this 4 column and the 1 row, so this is really going to be 41 in base 16, 41 in hexadecimal. Of course, 4 times 16 is 64, plus 1, which is really a value of 65. And so 65 is our capital letter A. And what you'll notice is that we've got our capital letter A, but we do in fact also have a lowercase letter a, which is a Unicode value or ASCII value of 61 in base 16. And so 6 times 16 is 96 plus 1, which would give me a 97. And that 97 is our lowercase a. And so we have a way to translate between our normal alphabet and hexadecimal codes in base 16 that we talked about in a previous video. Now, there's two ways that we'll recognize that a number is supposed to be hexadecimal, because notice that 41 and 61, they don't look in and of themselves hexadecimal. And so one of the ways that we'll see hexadecimal numbers is we'll see them with a starting OX. And this OX at the beginning tells us, hey, the number that's going to be following is in base 16, hexadecimal. So if I convert this, first thing I'm going to do is try and convert this 54. So I look at column 5, row 4, and that's a T. Then I've got this 45, so I'm looking at row 4, column 5, and that's an E. Then I've got 4C, so I go to row 4 and down to the C. Remember, C is 12. Then I've got 45, which we said was E. Then I've got 54, which we said was T. Then I have 59. 59 is Y. Then I have 50, so 5 and 0 is P. And I have 45, so over 4 and then down to 5, that's E. And so we see that we get the word teletype when we decode this, when we translate it from the ASCII chart that we have here to our standard English. So if I see OX, that tells me that I'm going to be dealing with hexadecimals. But there is another thing that I would notice, and that would be that if I saw this /U, the /U tells us that we're specifically talking about Unicode. And for our purposes, if I'm trying to translate to English, I really only have to look at these last two bytes, the 4 and the 7. So if I look at this 4 and the 7, row 4, column 7 is going to be G. Then I look at 72, column 7, row 2 is R. Then I've got 61, so 6 and 1 is A. Then I have 63, that's going to be a C. Then I have 65, which is E. And notice that these values actually allow us to distinguish between capitalized and lowercase letters, because capital letters are only going to be using these first two columns, but our lowercase letters are going to be using these last two columns. In other words, lowercase letters start with a 6 and a 7. So we had that was our G, that was our R, our lowercase r, I should say. This was our lowercase a, this was our lowercase c, this was our lowercase e. Then I have this 20, and I've got 2, 0, and that gives us this, which is a space. So I know that there's going to be a space here. This must be the end of one word and a beginning of another word. I have this 48, so if I go to column 4 down to 8, I get H. Then I've got 6F, so I'm going to do 6, and all the way down to the bottom is an O. Then I have 70, so column 7, that's a P. And 70 again is another P. And then 65 we noticed was an E. And then we have 72, so column 7, row 2 is an R. And so what I've got is Grace Hopper. Grace Hopper was a Navy officer, started during the World War II period, and worked with the Navy throughout the 50s, 60s, 70s, and even the 80s, and was one of the first programmers in America. One of the first people to program the computers. She invented computer languages, and she's a very good person to read a lot about. So I highly suggest you read about Grace Hopper. There's three things that I want to talk about here, and that's this notion of a space. So here, in order to get a space, I had to use the Unicode value 20 in hexadecimal, which, by the way, is 32 when we're talking about base 10. So there actually was a code for a space. If I was to go back and talk about the Morse code would have a series of dots and dashes, and then there would be a pause. So I would see some type of pause before the Morse code started up again. And so this pause would represent the space between words, or the spaces between sentences. And when I was looking at Braille, I would see the last letter of some word, and then there would be a physical space, and then I would see another letter of another word. So all of these three systems have a way of encoding spaces as well, but it's really difficult for them to encode things other than spaces. The encoding of numbers in both of these systems are very kludgy at best. They're basically added on. And any type of punctuation is going to be very difficult as well. The ASCII system, on the other hand, because we have here, there's really 127 different possibilities for all of these, actually 128 different possibilities for all these symbols. You see this section up here, and this section up here was actually used for formatting. So we would format here, and some of the things we see, BS, that's backspace. So 08 in Unicode or ASCII is a backspace. 0 and D would be a carriage return. Here I see a 1 and a B, and that would be escape. And all of these symbols do things with transmission of letters, either transmitting the letters starting and stopping, or acknowledging and synchronizing connections, or physically moving the cursor up or down or left or right, which is what all of these commands do. You also see our punctuation, and there's a very interesting relationship between the punctuation, because here is the Unicode value for the digit 1, but really if I was to hit the shift, the exclamation point is what's on top of the 1. And if I look at the 3, the pound sign is what's on top of the 3, and the dollar sign is what's on top of the 4, and the percent sign is what's on top of the 5. There's one little discrepancy here, and that's because on the older typewriters, the quotation was actually on top of the 2. But with the advent of the technology era, this @ symbol, which is a little bit more important, was put into that position. And you also notice the same thing with the letters. Here's capital A and here's lowercase a, 32 apart. Here's capital C and here's lowercase c, 32 apart. Here's capital Z and lowercase z, 32 apart. Here's the right bracket and here's the right brace, which is what I get when I hit shift while holding the right bracket. Again, 32 apart. And so I notice this similarity where the codes are related to each other. So, purpose of this video was to talk about encoding into a coded system, and the three codes we talked about was the Braille system, the Morse code system, and what we call ASCII or Unicode, which is used primarily with computers. And we talked about some of the advantages, some of the disadvantages, some of the difficulties, and some of the uses, why they were designed, and why they worked well for the system they were designed in. So once again, this is Mr. Potter. Thank you for watching. Have a great day.